This video is on lipids, fats and oils. Okay, so fats can be solid, as in meat, or oils, like the oils that you cook with. So this is to understand the structure and the function of fats and oils. There's a few questions on here, so if you go through, pause the video and see before you start looking what of these questions can you answer, and then come back and see if you can answer them after. So lipids is a general name for fats and oils. Lipids are non-polar molecules, so mainly hydrogen and carbon. Fats are solids, oils are liquids, and fats and oils are both tri, meaning three, triglycerides. So pause the video. Can you draw a triglyceride? At this point you probably should be able to draw one. So a triglyceride, the molecule on the right here, is made of, the glycerol has a 3-carbon backbone, and then attached to that 3-carbon backbone are the 3 fatty acids. So the fatty acid molecules can have different lengths of hydrocarbons, but there are 3 fatty acid molecules. You notice that's a carboxyl, so carboxylic acid, and an alcohol. So carboxylic acid and alcohol make an ester. So you need to be able to draw these. Notice that it's CO this way, COO. The ester's pointing towards the 3-carbon glycerol. So when you're trying to remember how to draw it, remember it's carbon, oxygen, carbon, and then your double bonded oxygen, and then there's the long chain. So the triglyceride, this is a particular name for the one where you have stearic acid. So we'll look at all the different fatty acids molecules. So stearic is the one that has 17 carbons and 35 hydrogens in a row, but there are a lot of others. You need to remember the ratio, so you need 3 of these for every 1 glycerol, and you make 3 water as well. So it's a condensation reaction where you produce water. I have seen a question where instead of giving you the glycerol, they expect you to know the glycerol and also the fact that it's a 3-carbon molecule with 8 hydrogens, 3 oxygens. So you need to be able to predict that glycerol is around and recognize a structural formula or just a plain formula. Okay, so yeah, the hydroxyl and the OH get together to make the ester. So this is how they look when you draw out all the hydrocarbon chains, all of these, all 17. If you write them out properly, you can see that they're long chains of hydrocarbon molecules. So oils, like oils that you get from fossil fuels. Okay, so our fatty acids can be saturated or unsaturated. So you've probably heard of polyunsaturated oils that are good for you, and we'll look at why unsaturated oils, where you get them from. So stearic acid is a saturated fatty acid. So the long chain of carbons, you remember the normal formula for a saturated hydrocarbon is every carbon that you have, there's 2 hydrogens for it, and then normally you would say +2, 1 for either end, but because you've only got 1 end left, a saturated one would be just +1. So every time you have a double bond, every time you lose 2 hydrogens to make 1 double bond, basically the formula is that you would have 2 less than that. Or if you have 2 double bonds, you would lose 4 hydrogens for each double bond. 4 hydrogens for the 2 double bonds. So some various places that you find fatty acids, different sorts of fatty acids. meat products, nuts, different sorts of oils, obviously, and seafood. They tend to be the things that you need to buy and to eat, I should say. All right, this was the old data booklet. They just gave us the formula. And we could work out from this formula which ones were saturated and which ones were unsaturated. So there's kind of two ways to work it out. If you have the carboxyl group separate, if it's not a straight formula with just carbons, hydrogens and oxygens, like this, a simple formula, if it has the carboxyl group separate, then basically saturated, you double it, and then you have to add one extra hydrogen for the end. So if you're working out if it's unsaturated or not, if you don't get, if we look at this one, double it would be 22, plus 1 would be 23. So it's saturated. This one, double it, would be 26, plus 1 would be 27. So it's saturated. So you could work down the list and find out if they're saturated or not. If they're not, if you double it plus 1 and you don't get that number, if you get 2 less hydrogens, then you've got 1 double bond. If you get 4 less hydrogens, then you've got 2 double bonds. So work down the list and work out which ones are saturated and which ones are unsaturated. Pause this video because I'll put the answers up now. So pause it now. Okay. So you see this one here. If you double it, you get 34, plus 1 would be 35. So 35 minus 29 is 6. In pairs, there would be 3 double bonds. Okay. The other way of doing it is if you get your formula like this, then saturated, however many carbons, so if you collect the hydrogen here and that, the carbon here and that hydrogen, collect them both, however many carbons you've got, then you just double for the number of hydrogens. Okay. So if in the exam you see some sort of strange sounding name and you think, I can't possibly do this question, I've got no idea what the formula is, what am I going to do? I've got linoleic fatty acid, what do I do? Look up the data booklets because all of the formulas are in the data booklets. Alright, so we need to know what omega-3 and omega-6 fatty acids, you've probably heard of them, that you need to eat them in your diet from fish, etc., that they're good for you. So what they are, if we have our carboxyl group over here, this is the alpha carbon. Alpha in the Greek alphabet is the first letter, alpha, and then I think omega must be the last letter. Okay, so omega-3 means 3 carbons from the end. 1, 2, 3, you have a double bond. Or omega-6, so 3, 4, 5, 6, you have a double bond. Okay, so omega-3 got a double bond, or omega-6. So if we have a look, which one of these are omega-3 and which of them are omega-6? So if you go down the list, clearly you've got CH2s over and over and over and over 10 times. So this one's saturated. CH2s over and over and over, this one's saturated. So in the old data booklet we only had the formulas, but in this new data booklet we've got the semi-structural formula. Same thing here. So this one, you've got the first carbon, and then you've got 4 CH2s. So if we go carbon number 1, and then another 4 carbons, then we're up to carbon number 5. So this carbon here, this carbon here would be carbon number 6. So it's not an omega-3 or an omega-6. On omega-7, you've got a double bond. Okay, so this is omega-7. So can you go down through the list and see which ones are omega-3, which ones are omega-6? Pause the video And I'll give you 10 seconds and then I'll tell you the answers coming up now. Alright, what happened with the answers? Don't know. Alright, so this one, if we go back, first carbon, then another 4, that's 5, and then this one is 6. So this one is linoleic acid, this one here. So first carbon, second carbon, third carbon. Okay, so this is an omega-3. This one, first carbon, and then another 4 carbons. So we're up to 5 carbons. And then this is the 6th one, so that's omega-6. If we go down here, this one, 4, 5, and omega-6. So this is an omega-6. Okay. There's the answers. Alright, the melting point of fats, just the same as with all of the other. The longer the chain, the hydrocarbon chain, the more dispersion forces there are between the molecules, between the U11s are finding this word difficult, between. So the higher the melting point. So clearly this has got the highest melting point. It's got 18 carbons, so a lot more carbons, a lot more dispersion forces, so the molecules are held together better. So basically these are all fats. No, this one's coconut oil, very thick oil. No, it's a solid. They're all solids at room temperature at 25 degrees. Okay, effect of the carbon-carbon bond on the melting point. So if it's a straight chain, clearly those 3 fatty acids can all be a nice straight chain and line up next to the next molecule, and so there'll be lots of dispersion forces all the way along. But if you have an unsaturated fatty acid, most of them are cis. So this would be a cis, and so the hydrogens are both on the same side, and that causes the chain to kink, so bend in the middle. And so you can't, if you've got a chain here lined up, then you can't bond, you can't form dispersion forces because this part here is too far away and this part here is too far away. So a straight chain here, the only place that you could get to bond is this one here. So they just don't line up, and so you don't get dispersion forces between them. So they're not held together as well, so you don't have to heat them very much before they become liquid, before they're not holding next to each other. And so unsaturated things with double bonds tend to be oils because they have weak dispersion forces. So if we have a look here, the more double bonds you've got, the less dispersion forces you have, so the lower the temperature before it goes from a solid to a liquid. So basically all of these would be liquids at room temperature, and it's not until you get here that it's a solid at room temperature. So skeletal diagrams, you need to get used to these. Every time there's a bend, there's so this OH, the oxygen is directly attached to this carbon here. And then there's another carbon, 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 etc., etc., etc. Carbon here, carbon here, carbon here, carbon here, and so forth. So this is a cis. So the 2 longer chains, these 2 longer chains are pointing in the same direction, and the 2 hydrogens would be pointing in the same direction, cis together. So it's kinked, it's bent. Alright, so if you see the trans, still got a double bond, but the long chain is on this side and the other long chain is on that side. So basically it's still a straight chain. So trans fats are like saturated fats. Okay. Essential fatty acids, just like essential amino acids, they're ones that we have to eat because we can't make them. And they're all the polyunsaturated ones. And that's why we should eat so much fish and seeds and things. All right, I might leave this actually, but I'll do